Hello, welcome back on my channel. Welcome back on question and solving for physics higher level paper 2 on year 2 2021, yeah, Monday 3 May. So don't go anywhere to sit on your desk and please watching this video until the end. Yeah, don't forget to subscribe. Okay, let me check number 1. Hope yes. Question 1 is two players are playing table tennis. Player A hits the ball at height 0.24 meter above the edge of the table. Measure from the top of the table to the bottom of the ball. The initial speed of the ball is 12.0 meter second minus 1 horizontally. Yeah, some that are resistant is negligible. Okay, we have velocity horizontally 12.0 meter second minus 1 and then height 0.25 meter. Then question A is so that time taken from the ball to reach the surface of the table, it's about 0.2 second. Okay, actually this is projectile motion. Yeah, they don't have any acceleration on the horizontally, but they have the acceleration of gravitational acceleration or gravitational deceleration. So we can put 0.24 to find both times. Yeah, we have h equals to ut plus or half gt square. Yeah, so we have 0.24 equals to, we don't have any velocity on the vertical one. Yeah, so when times t become 0 or half, we use g as 9.81 and then times t square. So t equals to root of 2 times of 0.24 is 0.48 divided 9.81. Yeah, maybe this is about 0.2 second. That's it. Okay, then question 1a. Yeah, now question 1b. Sketch on axis a graph showing the variation with time of the vertical component velocity vv of the ball until it reaches the table surface. Take g as 10 meter second minus 2. Oh, 10. Yeah, we use 9.81. It's okay, later we will use 10. Okay, they have velocity something on the 0.2 second, so maybe we need to find about velocity after 0.2. Yeah, we use formula wait, this is for the vertical component of velocity of vv. Yeah, so on the vertical they have acceleration as acceleration from gravitational acceleration. Yeah, this is about 10 meter second minus 2. So since you know that a is delta v for delta t, yeah, or gradient of graph for the function velocity and time. So we need slope. Yeah, we find slope that v over t is about 10. Yeah, so when we say this is 0.1 and 0.2, this is also on the 1 2. So between on the x and on the y, yeah, we just make a line. That line, they have slope as a 10. Yeah, so go directly 1 divided 0.1 equals to 10. Yeah, same thing with 2 divided 0.2 equals to also 10. Yeah, so you can decide that the line is like the one. Yeah, this is yeah, about that slope, or a is 2.0.2. This is about 10. Yeah, and then also 1 divided 0.1, it's about 10 also. Yeah, it means this is about acceleration. Yeah, acceleration of gravitational acceleration. Yeah, that's it. So the graph is like this one. Yeah, sorry, this is maybe like the here, this one. Yeah, okay, that's it. Yeah, so continue to other question. The next question, C. What C is, the net is stretched across the middle of the table. The table has length 2.74 meter, and the net has height 15.0 centimeter, so that the ball will go over the net. Okay, so maybe we will find about height. Yeah, or we find about distance with yes, the passing ball will go over the net. We need to find about this one. Yeah, this is like we need a half of net time. How much time is, yeah, after passing the net is. So like we find t. Yeah, this is a half of 2.74 and divided with velocity. Velocity is 12, yeah, meter per second. So this is about, wait, okay, 0.114, yeah, second. So after this, we find about y. Yeah, the height of net, is it still up then of 15.0 centimeter or no? Yeah, we use y equals to ut plus a half gt square. Yeah, u still 0 and t is 0.114. Yeah, exactly, this is 0. Yeah, plus a half gt square. So maybe we erase for this one. Yeah, so this is 0. Here is 0 plus a half g is 9.81 and times t square 0.114 square. Wait, we find first. This is 0.065 meter. Yeah, so you see this is like something with 6.5 meter. Yeah, centimeter, sorry. Yeah, 6.5 centimeter. So like height is sorry, this is height like 0.24 minus 0.065. Yeah, this is about wait, 0.175 meter. This is height below of the below of this point, like here, 0.175 meter. So they still passing the net, because this is 0.15, 0.15 meter. So like we have still here is 0.25 meter. That's it. So the ball is passing from the net. Okay, that's it. So let's check question D. The ball bounces and then reach the peak height 0.18 meter above the table with the horizontal speed of 10.5 meter second minus 1. The mass of ball is 2.7 gram. So I respose. Determine the kinetic energy of the ball immediately after bounce. The kinetic energy of ball immediately after the bounce, when on the floor. So kinetic energy on the tables, plus potential energy on the table after bounce back. This is kinetic energy after they have velocity 10.5, plus potential energy after they have 0.18. So this is 0. We come H is 0 on the table, and kinetic energy was kinetic energy after bounce back at height 0.18. They have of plus mgh. So this is equals to mass is 2.7 gram. We convert it to kilogram, and velocity is 10.5 square, plus mgh, again mgh. Mass is 2.7, convert into kilogram from gram, and gravitational acceleration is let's say 10, and height is 0.18. So this is in grade I calculate first. 10.5 square times 2.7 divided 2. This are 0. For the kinetic energy 0.148, and the potential is this about 0.048, 0.0486. So kinetic energy after bounce up is wait, this about 0.15 2, yeah, 3 only in Joule. That's it. Okay, and about question DI2, yeah. Player B intercept the ball while its peak height. Player B is hold a pedal rocket stationary and vertical. Yeah. The ball is contact with the pedal for 0.010 second. Some the collision is elastic. Calculate the average force exerted the ball on the pedal. State your answer to appropriate numbers of significant feature. You still remember about force? This is a change of momentum per time. Yeah. mv minus u, yeah, divided delta t. I think there is no change in velocity. Yeah. Change velocity come to stationary is 0. Yeah. So like here mass 2.7 times 10 to the power negative 3. Yeah, the velocity is come to 0. Yeah, from 10.5. Yeah, and divided 0.010 equal something with 10 to the power negative 2. Yeah. So when we calculate this is equals to negative 2. About 2.1. Yeah. This is about 2.1 Newton. Yeah, that's it. Okay, done for the question 1. Yeah, so we continue to question 2. What is it? Okay, you need to see first about the question if you want to read it first. A planet is in a circular orbit around star. The speed of the planet is constant. The following data are given. Mass of planet 8.0 times 10 to the power 24 kilogram. Mass of star 3.2 times 10 to the power 30 kilogram. Yeah, assume inverse. Distance from the star to the planet are 4.4 times 10 to the power 10 meter. Explain why center force needed for the planet to be a circular orbit. Yeah. Okay, this is to maintain in equilibrium force. Yeah. So like this is for maintain. Yeah. To equilibrium force. Yeah. The force between centripetal and gravitational force. Yeah. Centripetal force and gravitational force. Yeah. So it means if we draw it, let's say this is the planet and this is the star or sun. Yeah, this is, let's say this is star. Yeah, and this is the planet. So between planet and star, they have constant velocity in orbit, yeah, because they have two force in equilibrium, yeah. This is force, gravitational force, and the other one is centripetal force, yeah. So this means centripetal force, yeah, it's needed to make the equilibrium with the gravitational force, this, yeah. So the velocity is constant, the speed is constant. That's it. Okay, the big question is calculate the value of centripetal force. Centripetal force is M I think centripetal force shifting with gravitational force, yeah. Sometimes we use F centripetal, yeah, is M V square divide R, but we don't have any this, yeah, about force as about velocity or about speed, so we can use this is something with F gravitational, that F gravitational is G m divided R square, yeah. So F gravitational, yeah, G is 6.67 times 10 to the power 11, yeah. And G is mass of planet or mass of maybe star first, yeah, star is 3.2, yeah, times 10 3.2 times 10 to the power 30, and mass of the planet is 8.0 times 10 to the power 24, yeah, and divided with distance 4.4 times 10 to the power 10, yeah, and then square, yeah. So I will use the calculator. Yes, FG about with 6.67 times 3.2 times 8 divided 4.4 square. This is about 8.81, yeah. 8.81, yeah, times 10 to the power with 30, 60, 11 plus 54 minus 20, 45, yeah. This is 45, yeah, in Newton. This one, yeah. So between planet and stars, they have centripetal force as 8.81 times 10 to the power 45 Newton, yeah. We use the equation for the F centripetal means something with gravitational force, yeah. This one. yeah, by the equilibrium between them. Okay, that's it. Continue to the next question in still number 2. Yeah, what is it? A spacecraft is launched from the surface of planet to escape the star system. The radius of planet is 9.1 times 10 to the power 3 kilometer. So the gravitational potential due to the planet and the star at the surface the planet is about minus 5 times 10 to the power 9 joule per kilogram. Okay, gravitational potential, yeah, or we call it as the this is gm. Oh my god, sorry. Divided or yeah 6.67 times 10 to the power 11, yeah, and mass of the planet is 8.0 times 10 to the power 24, 8.0, yeah, this is 8.0 times 10 to the power 24 and divided the radius is 9.8 times 10 to the power 3, yeah, so yeah. 6.67 times 8 divided 9.81. Oh, this is about 5.8. Wait, I will check about G first, yeah. Maybe I have mistake about G. We check on the constant. Oh, there is no constant. G constant is because this is we get 5.8, yeah, 5.8, not 5.0, times 10 to the power wait, I will check about gravitational constant. Oh, I have mistake. This is about not 11, yeah, but minus 11. So sorry, this is minus 11. Here minus 11. Yeah. So this is equals to. Later I will change also the previous number. Yeah. To minus 10. Oh, this is in kilometer. Oh, sorry, I have mistake about this one also. This is in kilometer, so not 3. This is 6. Yeah, 6 meter. So this R is 5 point. Wait, yeah, I will calculate again. Yeah, 6.67 times 8 divided 9.1. This is about 5.86. Yeah, 5.86. 86 times 10 to the power 24 minus 11 minus 6. This is about 7 here. 7 joule per kilogram. This is about planet. Yeah. How about stars? Yeah. A star, yeah, we have this 6.67 times 10 to the power negative 8, and stars we have mass is 3.2 10 30 3.2 times 10 30, yeah, and divided with R is this, yeah, 4.4 times 10 to the power 10. Okay, so I calculate again. 6.67 times 3.2 divided 4.4. Yeah, that's about 4.85. 4.85, yeah, times 10 to the power 30 minus 11 minus 10. Waalaikumsalam.
Ya Pak.
Dek,
Ya Pak.
joule per kilogram. So when we adding about two potential, this is like something with 4.85 and then 586, yeah, times 10 to the power 9. Or yeah, this is about 4.85 times 10 to the power 9. Yeah, it's around 5 times 10 to the power 9 joule per kilogram. That's it. Okay, estimate the escape speed of spacecraft from the planet star system. Yeah, this is we escape something with root of 2 potential. Yeah. Yeah, root of 2 times 4.85 times 10 to the power 9. Yeah. This about It development. It's about 9.84. Yeah, 9.84 times 10 to the power 4. Yes, the force 4, yeah, meter per second. Yeah, that's it. Okay, done. Let's also check, continue to the next number. A mass of water 1 kilogram is brought to its boiling point of 100 degrees Celsius using an electric heater of 1.6 kilowatt. The molar mass of water is 18 gram mole minus 1. Estimate the average speed of the water molecules in the vapor produced. Some the vapor behave as an ideal gas. Ideal gas, so we use kinetic energy, average speed. We use we can use about V as 3 Boltzmann constant divided M. Yeah, between the Boltzmann constant, same thing with Avogadro number times constant. Oh, sorry. With oh no, we can with K is 1.38 times 10 to the power negative 23. Yeah, K Boltzmann constant K is 1.38 times 10 to the power negative 23. Yeah, and T is 3 is 100 plus 273, something like 373 Kelvin. And mass is we have molar. M equals to with gram mole times molar wait 0. Oh, we have 1 kilogram. Wait. Oh, this is same thing. V, yeah. V is root of 3 Boltzmann constant 138 times 10 to the power negative 23, and then we use Avogadro number, yeah, 6.2 times 10 24, yeah, because we use this, yeah, as a 0.018, yeah, from mole divided 1 kilogram, and this is temperature 373, yeah. Yes, then I calculate first, yeah. 3 times 1.386, and then equals to it's about 718, yeah, 720, maybe 720, yeah. We round it, this is about 720 meter per second. That's it. Okay, what about question II? State one assumption of kinetic model of ideal gas. One assumption, maybe about collision, yeah, collision between particle, yeah, are elastic, yeah. Okay, this one. This is elastic collision. Sorry. Collision between particle are elastic. And maybe the other one, about force, yeah, or there is no intermolecular force, yeah, no intermolecular forces. Yeah, maybe two, yeah, enough two, yeah. Okay, that's it. Okay, now let's check question B. A mass of water, I assume in first, yeah. B question. A mass of 0.86 kilogram of water remains after is boiled for 200 seconds. Estimate the specific latent heat of evaporation of water. State an appropriate unit for the answer. From K equals to ml, yeah. K equals to L. K means PT equals ml. So L equals to P times T divided M. Yeah. L equals to we have P is 1.6 kilowatt, yeah, or 1600. Is it correct? 1.6, yeah. Yeah, here times T is 200 second, mass is 0.86, yeah. But okay, this is about 2.3 times 10 to the power 6. 2.3 times 10 to the power 6, yeah, joule per kilogram, yeah. Yeah, that's it. Okay, done. Question I explain why the temperature of water remains at 100 degrees Celsius during this time. This is about all energy, yeah. All of the energy added is used to increase the potential energy of the particle bricks, yeah. So all of energy added, yeah, this all of energy needed, yeah, is used to potential energy increase the potential energy to the particle bricks, yeah, to the particles or about bonds of intermolecular bonds, yeah. Intermolecular bonds. That's it, yeah. Okay, I think enough. We go to the next page. Question C. Whoa. Question C is the heater is removed and mass 0.30 kilogram of a pasta at negative 10 degrees Celsius is added to the boiling water. Determine the equilibrium temperature of the pasta and water after the pasta is added. Water heat transfer unnegligible. Okay, we provide specific capacity of pasta is 1.8 kilojoule per kilogram degree Kelvin, and also specific heat capacity of water is 4.2 kilojoule kilogram minus 1 Kelvin minus. Okay, we find wait. This is like black principle, yeah. Energy change on the water, yeah. Same thing, energy change on the pasta. Okay, let me check. This we use MCT, yeah. Use MCT, then Q water, yeah, equals to Q pasta, yeah. This is mass of water is how much is 0.86 kilogram, 0.68 kilogram, 0.86 kilogram, and specific heat of water is 4200, and delta T of water, this is because until 100 to from the something, yeah, on the pasta is, yeah, equilibrium temperature, yeah, T, yeah, this is equilibrium temperature, equals to mass of pasta is 0.30, and pasta is 1800, and delta T is T minus 10, yeah, plus 10. So we calculate this, yeah, we calculate this. What about this one? Yeah, T is T equivalent is T equilibrium is with 0.86, okay, 0.3 times with, yeah, I still calculate. Okay, done. This is about 8569, 8569, yeah, maybe we around it. This is about 86, yeah, degree Celsius. That's it. Okay. Question D. Question D is the electric heater has two identical resistors connected in parallel. Okay, the diagram shown that the circuit transfers 0.6 kilowatt when switch A only closed. The external voltage is 220 volt, yeah. So that the resistance has resistance about 30 ohms. About 30 ohms. We use power, yeah, we can use the power one. Power equals to V square divided R. So R means V square divided P. We have V 220 square and divided 1600, yeah. This is about with 200 square divided 1600, about 30.25, yeah. Yes, but this is about 30 ohms. Done. Yeah, that's it. Okay, done. Yeah. We use formula P equals to V square divided R. One more question in this number. Calculate the power transferred by heater when both switches are closed. Oh, we use total. We back again. Still use the formula P equals to V square over R, but R, yeah. Oh, sorry. R is equivalent between 30 and 30. This is equals to 15, yeah, ohms, yeah, parallel, yeah. So power means V square divided R, so 220 square divided 15. Yeah, this is about, wait, 220 square divided 15. Oh, 326, 3000 226 watt. That's it, yeah, it's about, yeah, maybe around 3225. Yeah, this is about this. Okay, done. Continue to other question. Question 4. Go. A planet orbit at a distance d from a star. The power emitted by the star is P. The total surface area of a planet is A. Explain why the power incident of the planet is O. Okay. For the P divided 4 pi d square, this is power, yeah, received, yeah, by the planet at a distance d, yeah, at the distance d, at the at a distance d, yes, this is power, yeah, power received by the planet at a distance d, and then the coefficient of A divided 4, yeah, this is about area, projected area, yeah, projected area. Projected area, or maybe cross-sectional area, yeah. Sectional area. Of the planet. Done. Yes, that is, yeah. I still remember when intensity is power divided area, and then the area is 4.3 pi r square. Yeah, maybe something still relate with this. Still relate with this. Okay, question II. The albedo of the planet is alpha P. The equilibrium surface temperature of the planet is T. Derive the expression T equals to where E is emissivity of the planet. Oh my god. Reuse power as wait. If you still remember, I scroll up first. Power is a Stefan Boltzmann constant, a T4. Okay. Then wait. And we have expression of I see. Then we can use like the albedo planet is AP, so T4 equals to P E Stefan Boltzmann constant over A, and this is time with alpha P. So when A we can change into 14 PD square, without A. Oh, yes, because we change from this one as a one. This is divided A, sorry. As the A equals to 1 divided with sorry. One over A, 1 over A as 1 over alpha P minus VD square, so we include this from here. Then so T as the root of 4 P1 alpha P divided 6 PD square E Stefan Boltzmann constant. Yeah. I think this one. I use this here from that A equals to 16 PD square divided 1 of the albedo of the planet. Yeah, that's it. Okay. Okay, you may see this first here. Okay, big question. One more question on this number. On average, the moon is same distance from the sun as the earth. The moon can be summed to have emissivity E equals to 1 and albedo alpha m 0.13. The solar constant is 1.36. Calculate the surface temperature of the moon. We use this one, T as root of 4 by T is root 4 of I'll go here. T is of the power over area is 1.36 10th power of solar constant. Wait. Oh, this is solar constant. Okay. 1.36 times 10 power 3 and 1 minus 0.13 divided wait. Emissivitas is 1, Boltzmann constant. This has become 4, and then Boltzmann constant is Stefan Boltzmann constant 5.67 times 10 to the power negative 8. So when we calculate this number, it's about 268.75 Kelvin, or this is around 270 Kelvin. That's it. So maybe you have a question why this is 4. Why this is 4. This is from constant 13.6 times 10 to the power 3. This is in watt per meter square. It means like the area, yeah. You know the area is 4 pi r square. It means 4 pi d square over, oh sorry, oh sorry, PD square, so become 4. No, sorry, because this is 1.3, yeah. P over A means 1.36 times 10 to the power negative the power 3. This is already in watt per meter persegi, ya. Yeah, why we have 4? Yeah, because this is like 16 PD square divided 4 PD square. Yeah, so we can get 4 1. Yeah, so on this side. They asked me about solar constant. Yeah, solar constant. That's it. And emissivity 1. Yeah, we just like no type 1. Yeah, because same thing with this number. Yeah, anything times 1 equals to that number. Okay, just continue to number 5. Yeah. We have device send an impulse of electrical energy to maintain a regular heartbeat in a person. The device is powered by the alternating current AC supply connected to a step-up transformer that charges a capacitor of capacitance 30 microfarad. Okay, transformer, diode, switch AB, capacitor, and heart. Explain the role of the diode in the circuit when the switch is position A. When the position A, the only the charge of capacitor current must be direct. Yeah. This to charge a capacitor current, must be direct, yeah. um diet will only allow, yeah, will the direction or current to flow in one direction, current to flow in one direction, yeah, it is, yeah, in one direction. Or because we don't have other diet on the upside, yeah, so the diet provides half rectification, yeah. The diet sorry provide oh, sorry, half with rectification, yeah, only half with, yeah, only half of rectification, yeah, that's it.